Okay, welcome everybody. It's great to be here. I hope you had all a good trip. So I talk today about something new that we have been working on in our group or have been thinking about. And this is from going from geometric safety to semantic safety in robot learning. And I took the talk title, the workshop title, to actually kind of challenge a few perceptions. So the workshop is called Towards Reliable and Trustworthy Embodied AI in Everyday Scenarios. And when I hear everyday scenarios and I don't think much about it, this is what I think about. And I think I really want to challenge this because this is not what we should think about if we think about everyday robots, because robots are already working every day 24/7 in many, many applications. And there are many applications on the horizon that are much closer to being realized than these ones. And the same like this, right? I mean, of course, I think these are very, good science fiction type goals. But we should also see where's the low-hanging fruit, where can we really deploy robotics today and every day. And so when I talk about real everyday scenarios, of course, manufacturing industrial automation is everywhere, and it has been around for a long time, but logistics and warehousing is becoming more and more automized as we speak. And there are many interesting simple applications in service and consumer robotics, in healthcare, and in agriculture, autonomous vehicles. So if you kind of see my talk today, the robot platforms that we work on are closer to those than kind of the futuristic everyday scenario. And I do think it's really interesting to kind of see where robotics takes us next in the next years. And so the type of robots I will show you today, some of them are shown here. So mobile manipulation platforms we are working with, so mobility plus manipulation, but not with legged robots, but wheeled. But nevertheless, the algorithms are very similar. Robots that can be in more human-centered environments, such as kitchens, but a lot of the work we have been doing is also on self-driving, on the road and off the road, as well as on the sidewalk, most recently. And so Sequoia is also here at the conference, so if you are interested in sidewalk robots that interact with humans, you can find him at the conference. And finally, we've also looked a lot at warehouses. So these are kind of the type of robots we have been working with, and what I also think are everyday robots. Then the second part of the title, reliable and trustworthy embodied AI. This is something that is part of our kind of research DNA for more than 10 years, because whenever we started deploying machine learning on real robots, we were caring about reliability and trustworthiness. And for us, this meant safety through constraint satisfaction for the most part. And so I think this is the direction I want to go. So when I talk about reliable and trustworthy, this usually means constraint satisfaction or safety through constraint satisfaction. And so there are three kind of types of safety I'm going to talk today about. And one is dynamic safety or stability. And so in the scenario here to the right, I just try to find something which you may be able to remember. So dynamic safety here means that you hold that the hand is held steady, right? So if this task would be done by a robot, dynamic safety is like you steadily hold the water. Geometric safety, which means, yes, you have to do the task such that there is no collisions. Okay? And I think this is something that is the typical, I think, safety that we see also in safe robot learning, is geometric safety added. And then finally, there's semantic safety, kind of understanding the whole situation, that this is a dinner table, that there are multiple classes, that I may need to be careful with kind of putting the water in the class because there are kids around or something else. So understanding the whole context and making judgments, right? And we know that from computer vision, we can understand this situation now. So there are lots of large foundation models, or even before deep neural networks, that can tell us what and so on. And so these three types of safety kind of is what we are interested in, and especially kind of expanding beyond geometric safety, which means collision freeness. And this is, I think, something we also saw in Sebastian Schero's talk earlier today. I think he also deploys robots in the real world, so safety really matters, but typically he focused also on geometric safety, so finding an off-road path without collisions, for example. And so what I'm going to do today is kind of take you on this trajectory from geometry, constraint, control, and learning. So where constraints are predefined offline, for example, from maps, so you know where are the walls, the obstacles, etc., to online constraint learning, that we close the loop with perception to determine these constraints from computer vision, and finally expanding this to semantic safety, that we kind of derive safe actions from high-level semantic understanding using vision and language. And so, of course, this kind of all goes in the direction of increasing complex understanding and embedding this into the safe decision-making of robots. Okay, so let's get started. Try to kind of keep it very simple with simple block diagrams. So I hope you, you're still a bit interested. So the super simplest case is, right, I have a model-based model that can tackle constraints, and those are defined and given. So predefined geometry constraints. That controller also has access to the full big assumption, right? But then a constraint controller makes sure that these predefined geometry constraints are satisfied. And so the typical approach for this, and this, I mean, was not a given that there's a simple approach to actually achieve this, is model predictive control, right? So in model predictive control, if you have the model of the robot and you have the constraints all given a priori, it solves the constraint optimization problem at every time step and can guarantee constraint satisfaction. But there's still a lot to be done, even in this case. And a tractable formulation of the constraints is key, or generally how you formulate this optimization problem such that you get efficient solutions that you can compute like in milliseconds. So I show you two examples that I just want to highlight. There's still even a work to be done here when the model is known and the constraints are. And you see this at the two examples. So we have one is on non-prehensile object manipulation, which I will show you in a second. And this was published in 23 and 25. And then we have another one on swarm coordination, where actually the geometric constraints are also other drones in the environment. And both of them kind of tackle the constraint part very cleverly. And therefore, for example, the swarm coordination application is the fastest right now available. So, and we kind of bet the best solution by a 2-digit percentage. And yeah, so let me show these just to show you. Can still do a lot here. So this is what non-prehensile manipulation means. You don't grasp the object rigidly. This is always important because you clearly have to transport, usually, in the life of a robot, it needs to transport objects that are bigger than its own hands. Right? So the hands usually have very limited. Take the geometric constraint that these objects need to be on, stay on the tray and not slip into account in a model predictive control approach. We can get very good and elegant motions for a variety of different objects without even knowing the objects in too much detail. So here we kind of cleverly embedded the constraints in the control. Then the other one is the swarm transition one. So here you see drones transitioning in a constrained kind of environment where there are obstacles, and they also have to avoid each other. So they can avoid static geometric constraints, the pillar, and handle dynamic constraints. We also show here where we also track the person, and the drones can fly around and coordinate their motion to not collide with each other. This is all what I call geometry constraints or geometric safety. Then in my group, and with my whole team, we have optimized these types of approaches by expanding from just a constrained model-based control to constrained learning control. So where we can consider geometry constraints, but we optimize the control, so the actual decision making of the robot based on data. Okay? And there are different approaches. I just want to mention this. You can either have constraint satisfaction during the learning already or after learning. And those approaches exist, but in this simple setup, quite a lot of progress has been made over the last 10 years. And we try to summarize this in our survey paper, which you see here at the bottom, Safe Learning in Robotics from Learning-Based Control to Safe Reinforcement Learning. And so, yeah, there has been a lot of progress been made, but it still looks quite simple, right? This block diagram, you get the full robot state, you get the geometry constraints, you just optimize performance based on learning. And I just show you a few examples how this can look. Right? One is here, actually, the safety is only guaranteed after learning. So the robot practices this task up the pose and then goes down. So this is a method where the constraints are guaranteed after learning. And then we can do different configurations. And this is now almost 12 or 13 years old work. We can do other more clever things. So here, yes, basically how this works is there is an inverse model learning block, the green one, that is attached to this general baseline controller, and the underlying controller guarantees safety and compensates for the random effects. And we really use the learning just to optimize performance, right? While still guaranteeing that geometric safety is guaranteed. You can do other approaches where you directly learn the probabilistic model of the robot. So you directly embed learning and decision-making into one block. And because we use a probabilistic approach such as Gaussian processes, you can also guarantee both constraint satisfaction and stability, so dynamic safety. And this is an example. If you have seen my work, you may have seen this before, but here we try to follow a path, and there's enough model errors such that a purely model-based approach would not work. But then in this kind of uncertainty case, where we model the uncertainty in the system and learn from data, we can actually try this path safely from the start. So this is actually guaranteed safety under some assumptions, of course, during learning. So we can guarantee constraint satisfaction during learning. Here in this case, it means to stay within the path bounds, which you see on the right plot. And you make sure that over a prediction horizon with a very high likelihood, you stay within this path bounds. And then over time, you get to know the model better, and you can try faster while still guaranteeing that the constraints are satisfied. Again, these are geometric constraints, right? These are bounds on the path that we have predefined before. We actually took this robot also through a long, kilometer-long off-road path. And again, there we had to predefine how wide the path is at every section and give this to the algorithm. But then it could learn and use the learning to improve performance while always guaranteeing safety. And here's one other one I wanted to show. We can also use this same type of idea of a probabilistic learning model to safely tune controller parameters. And so that is also highly safety critical, right? Because if I try wrong controller parameters on a flying vehicle, it could crash. And so this type of probabilistic approach also allows you to do this. Here we had constraints that the vehicle should never get too close to the ground. And our approach guaranteed that. And then finally, the last one kind of in this geometric constraint is that we modify, and this is the kind of orange box, modify the output. So we modify the output of a learning block or a learning controller, which is highlighted in green, to guarantee safety. So we modify actions minimally to make them safe. So this is the third approach you can do to guarantee geometric safety. And this is also a very recent work you can see here at the conference. But the fun part is actually that if you kind of do reinforcement learning and not visit unsafe states in the first place, so you don't go where there are possibly constraints or safety violations, then you're much better, faster in convergence. So here on the left, you first see how many kind of constraint violations we have during training, and the red one is basically the one we propose, and it has no safety violations during training. So it guarantees the geometric constraints. But then you see on the right that the red curve is also the one that converges the fastest to the best policy. So meaning that, yeah, you probably, at least in the scenarios we looked at, you can learn faster if you avoid going where it is unsafe in the first place. And I think this is something, I don't know, that we do all the time with kids, right? Kids learn a lot, but in the framework, we allow them to do it. We don't allow them to just jump on the rope because that would be unsafe. And likely they learn better what is a safe, good action if we do these kind of interventions. Okay, so this is a work you can see here. And to summarize this, in this whole framework of learning to improve performance while guaranteeing constraint satisfaction, we did a survey paper on safe learning in robotics. We also did a benchmark suite, state control gym, where quite a lot of these approaches are implemented. So if you ever want to work in this direction and you want to compare against an existing approach, I go there because likely it's implemented there already and you can just take and compare against it. And then over the time, we also had different workshops and talks, and there can all be found on the SafeForwardLearning.org. So this was the case when we do machine learning, but the geometric constraints are predefined, right? So this was the bottom left one. So we have then expanded our work towards, like, can we actually get this kind of geometry from perception? And of course, this is possible, but often people do either SLAM or control. And so, yes, we did some work in this direction. And so the simple block diagram that I showed you before now looks like this. So the robot produces sensor measurements. They go into a mapping and state estimation block. And we get both the robot state, but also online learned or online extracted geometry constraints. And then we can take them for learning control. And I just showed two examples. The first one is actually here at the field robotics workshop today in the afternoon. And the other one, yeah, you can look up the papers at the link at the bottom. So, wait. Okay, so yeah, here you see at the bottom left how it is mapping in real time, and a mobile manipulator is doing a full body motion control in this environment and avoids the geometry constraints. And then here actually we even modify the environment such that we can simulate semi-static environments so that things change over time. And so here you see how the map is kept consistent and the robot performance is adapted based on the change in the geometry. So here the boxes shift again, and now the robot moves the arm again differently. So basically, we can deal with, semi-static environments both on the mapping side as well as on the full body control side, and we can guarantee that the robot, stays safe and satisfies those extracted constraints. And so finally, these are just basically the preparation to the main thing I think that is really interesting now. We know that we can extract this geometry inferred perception online. It's sometimes a bit challenging to do this in real time and also adapt your controller, etc. But I showed you we can even do this in semi-static environments. So meaning environments where things change over time. Right, so environments where the approaches that I showed you at the very beginning, the geometry constraint control and learning, where the constraints are predefined ahead of time, would not apply. And finally, the goal now is, can we really fully leverage what the perception system can provide us in terms of information to extract safe actions from this? And so the idea here is to have derived safe actions from high-level semantic understanding using vision and language. And I would say we have just done some first steps towards this. But here the idea is that we also obtain a semantic context, usually from also the sensor measurements of the robot, but maybe also more. Right? This could be other sources of information. And so the question is really, how do we specify common sense safety constraints beyond geometry of the environment? And so here are a few examples, and the work is linked at the bottom, is can a robot, detect from the semantic context that you shouldn't put a metal cup into the microwave, which is on the left, or you shouldn't put maybe a bottle on top of the eggs, which is shown on the right. So basically that we enable a robot to understand the environment and make good decisions based on understanding by kind of knowing what the objects are and where they are in the environment around the robot. But then you could also extract more. You can extract how they are related or other questions, what is important for the task. And this is basically where you can embed large language models as they are into robotics by basically saying, just describing the scene to a large language model and asking it about, what the robot should be careful about or what is important about this environment, etc. So I think this is basically the vanilla large language models can be used as another source of information. So we don't use kind of everything in a vision language action model, but instead we use vision, text, audio, possibly in the future touch or other information to understand the context and the semantics, like what the robot sees, like a human can do, and then use this for safe actions. And so I think this is basically the big question mark, how we then translate this back into safe actions. And so here's what we have done so far in this first work. I'll try to kind of slowly go over this. Yeah. And also check the time. So in this first work, we take RGBD images and camera poses, and then do segmentation. Open vocabulary segmentation, it basically tells what you see, right? And then also where you see it through the environment map. So you have a 3D point cloud, and each kind of set of points has also a label. For example, this is a laptop, this is a bottle, etc. And then you can get semantic constraints through prompting a large language model. So for example, you can describe what you see, you can prescribe what you want to achieve, and then ask a large language model about possible semantic constraints. So as a result, then you have geometric constraints, something that we had throughout the talk, and also some semantic constraints. And what they can be, I'll show you in the video in a little bit. So for example, you could ask, the information could be, you should not move a full cup over a laptop, but maybe around the laptop. It could tell you if the sponge is dry, no problem, you can move it, being too considerate. And other things like this, right? There's a lot of understanding of the world embedded in language. And you can try to extract this for the specific situation that you have. How we did this first work is that there's actually kind of a learn policy or a teleoperator here at the bottom left. And it kind of provides the initial motion, and the semantic safety filter would modify that motion to make it semantically safe. So right now it is basically just modifying a given action. It's not designing an action from scratch, but modifying a given action to make sure nothing dangerous happens. And so what could these kind of semantic constraints be? It could be unsafe spatial relationships. For example, metal cup should not go into a microwave. Could be unsafe poses, meaning that, for example, you shouldn't tilt a cup that is filled with water. Or it could be other kind of cautious behavior, like don't move a lit candle around balloons, things like that. So these are the type of unsafe behavior. And then we match this into the control approach as real constraints. And so the details you can find in the paper, but basically we try to translate this kind of semantic understanding into something the robot understands. And I think this is also still an open question how you best do this. But we did this kind of with a control barrier function approach and still in an MPC setting, so model predictive control. And then here are some examples. So so on the left, without semantic constraints, and on the right, with constraints. And you see, we only kind of modify the action to make it still safe. We don't actively design actions right now, which would be the next step. Right now, the operator wants to put the bottle on the X, but our semantic filter makes sure that this is not happening. Or the same here, like a metal can on possibly a hot stove, right? So the semantic constraint would just say stop, could be dangerous. Again, I think the next step would really be active motion design instead of just preventing bad things to happen. So here it stops the fork. So this was one of the works that we started in the direction of using the semantic understanding of the environment and translating this into safe actions. So going towards a semantic safety instead of just geometric safety. So what is next? I think there's so much to do. I do still believe in a modular approach, given how diverse our environments are. I think kind of right now we don't have enough data often to kind of deal with the diversity, but approaching semantic safety in a dynamic environment, I think is very interesting. So right now we kind of extracting what all the objects are in the environment takes a bit of time. But in the end, we have dynamic environments where people and objects and everything moves. Then even a broader context understanding and full multimodality. So right now we use vision and we use large language models, I think, and those also separately. So there could definitely be a lot being done for multimodality in terms of multimodality. And as I said, also in terms of active motion design. Semantics can, by the way, also be used on the mapping side or perception side itself. This is when we did the semi-static mapping. We actually took into account which objects we see and which objects are moving more likely than others. And that helped us to provide a consistent map over the long horizon. And so I think, so while I talked about semantics for kind of making safe actions, they are also important to have a consistent perception model or persistent and consistent model of the environment from a perception perspective. So yeah, when we kind of mapped in more dynamic environments, we took into account which objects can move and which objects cannot move. So we took account that semantic understanding as well. So yeah, I hope I could kind of convince you that we should definitely, as a field, go beyond geometry constraint, control and learning, and towards a concept where we talk about semantic safety and semantic understanding. Thank you.